Hi guys, welcome to this video on this is the third part of a series of sessions where we use Python to learn some astronomy concepts. Um, in in today's world, most of the data are available to the public. In this open source world, we can easily get data like like in the earlier days you needed a telescope and you need some resources like CCD camera to get the raw data and then process it to generate beautiful images. But in case if you don't have an access to a telescope, like you can always do research by accessing remote telescopes and just by writing a proposal, and you can do stuff with that. But the basic starts with working with publicly available data. Like today we will actually go through some ways of getting the data, and then once you get the data you need to process it, you need to analyze it, right? So the main programming language which we'll be using for the set of sessions will be Python, because Python is the most popular language and easy to use. And in Python specifically we'll be using this module called Astropy. So the Astrofile was a project. It was developed by the astronomy community to ease to ease working in astronomy. So there are a lot of functions and libraries which will help simplify the tasks and work efficiently in an astronomy problem. So you need to install this library to proceed further. I hope you have already installed some basic packages like NumPy, Matplotlib, and let's say SciPy. We won't be using SciPy much, but yeah, we might. Okay. You can install it in various ways. One of the way of installing it is just using pip. This is possible in any Linux distribution. You can just try pip install Astropy, you'll be getting it. In case you don't have in case you're using Windows but you already have Anaconda installed, it's recommended to install Anaconda if you're using a Windows distribution, because it already has a preloaded Python packages in it. You just need to use conda command to just install Astropy. Okay. So yeah, I just install Astropy before proceeding further. So you can use the video to actually understand the Jupyter notebook, which will be uploaded in the GitHub page, and the link to that could be found in the video description below. Um, so you can just open that side by side and then watch the video or listen to my commentaries so that you can understand the notebook better. Okay, let's proceed. So what exactly is a FITS file? So the heading suggests it's FITS handling. So it's FITS file handling in Astropy. So you might be seeing some images of, some various astronomy images, like let's say M41. Uh, no, let's take something. Okay, this is M41. So this is a very beautiful image of this particular cluster. So you will be seeing such images, right? So these are actually PNG images, like these are PNG or JPEG. These are very the size of such files are very less. It doesn't contain a lot of information about each and every star in the cluster. It's just a visualization of the overall image. Like you can just say that okay, it's just a bright stars over there and it looks beautiful, but you can't do much science with it. It's just a image to look at. But if you're working with FITS file, which is the staple way of working in astronomy, astronomical image processing, where FITS file will contain I'm sorry, what is it? Yeah, they have this extensions of data. Like for example, you can add informations like about the instrument used for getting the image, like the name of the telescope, the various parameters of the telescope, like which will be useful to compute something like, let's say, luminosity, integrated luminosity, where you need the area of the telescope and so on. That will be stored in that same file as that image. The file will contain the pixels, I mean the image pixels, which will contain the brightness values. It will also contain this kind of metadata, which has a lot of other informations, like the date when the image was taken and so on and so forth. So that's the reason why we use FITs, because FITs files support a lot of extra informations inside the same file. Okay. So today we will be using a FITs file, and I'll show you um, how to get a FITs file. So we will be using this famous um, database for astronomy called SDSS, Slow and Digital Sky Survey. You can just directly go to this link. I'll just copy paste the link over the in the notebook so that you can easily access it. Right, you just need to go to this single field search. This is the easiest way to search an image. I mean, yeah, I guess, yeah. There are much harder ways, but they're more efficient. Like you can write a query in SQL and do that. We will actually learn about SQL in the further sessions. So today we will look at M42. Okay, M42. I just need to type the name. So yeah, you can either search by the object name, or you can give the area and declination, which are the coordinates. We'll come to area and declination in a while, but just for now you can just take it as the coordinates of those objects on the celestial sphere or on the sky. And then just press submit, and you'll get just a visualization of the image, and you will see a band of instructions. Like you can download either the JPG image, which will be just an image, doesn't contain any data, whereas you can download the U band fits, G band fits, different bands fits, and the fits file is what we want for our analysis. But you can observe that what are these bands. Like you can see that one is a U band, one is a G band. So these bands corresponds to the filters which you use for observing the particular astronomical object, because it's always useful to instead of focusing on a wide range of spectrum, you can just use a filter and focus on, let's say, from wavelength lambda 1 to lambda 2, or let's say in the green part of the spectrum, and just get the information in that spectrum. Then you can combine that information of G with, let's say, information you obtain from the R band, and then you can make a composite image, and then you get more information out of it. That's how you make that's how you actually see such image. Like, this is not what you observe in a raw form. In a raw form, you just see black and white image, that's all. But you process it, I mean, you give it color and make it an RGB image. We'll see how to make an RGB image in a while. Okay. So yeah, just search it and download these files. So we will be using U, G, and I for our analysis. Just download them. You can just click on them, U, G, and I. Just extract them to the desired folder where you're working in. Just extract them to that. So I already extracted it here. You will also find it in the GitHub page. I'll upload it soon. So yeah, so we got the file. Now let's open it in Python. First of all, we'll obviously import the basic modules which you need, like NumPy and Matplotlib. So I imported them. Then we'll import Astrofile. So this is how we import fits from Astrofile, because we are interested in that particular library. So from astrofile.io, import fits. Okay. First, let's open the fits file. It's easy to open it. This is a simple command, fits.open, and the frame, the fits file. So here I'm opening the U band. You can open G or R This is just to give you an idea of what a fetch file actually contains. So that's, so we can open anything. Just run what is actually M40. So it shows that it's a fetch.hdu.image.primary object, and then something called image hdu object at something something. Yeah, so you can see that it's actually four different entities, right? One, two, three, four. So what are these? So to get a better idea of them, you can just run this command M42, which is the thing which is the object used for opening the fetch file. Just use .info and see what the fetch file actually contain. So first of all, it contains this primary header. So a fetch file will contain this extension on extension on extension, like a block on a block, and each block will contain a header file followed by some data. The primary block usually contain, the main data, like the image will be contained in the primary data. The extension might have some other information. For example, it might contain some information about the telescope, something about like some binary data and stuff like that. So here the primary data contains a float 32 data type object, which means that okay, it actually has the image. And then there are other other extensions like bin table hdu, image hdu. Yeah, so we'll work on the primary thing because that contains my image. So if I just run M42, so this is the 0 number is 0 here. So if I run M42 0, it shows that it's a hdu.image.primary hdu. If I run the header file, so the header shows some information, like you can see some informations like rotator position angle, the angular velocity of the rotator, array of telescope, bore side. So these are all the various information. You can learn more about it from the source where it got the data from, but these are irrelevant for our analysis for now. Okay, let's see what the second extension contains. So this is the first guy. This is this one. It doesn't have a name, just a first extension to that. It has some image extension, something, I don't know what it is, but it's not useful for us. The main useful thing in this block is the primary block, and I already got it here. So I just type data equal to M42 data. So I already got the data. If you run the type of the data, you can see it's a NumPy array, which is good news because I already know how to work with NumPy array. It made my life simpler. First of all, let me just check the shape of the array. Run data.shape 1489 cross 2048. That's pretty huge. Basically, these are the pixel sizes, like it's a resolution, you can say. You'll see the data type, it's float 32. Again, float is a good variable to work, good data type to work with. Now let's print some statistics, basic statistics of the image, like the minimum value of the pixel, maximum value, and the mean value, standard deviation, and so on. So this is some information you get, like the maximum value is 552, minimum value is minus 0.3, mean is something, standard deviation. I'll just plot this. So this is a 2D array, right? To plot a 2D array, plt.plot won't work because plt.plot was for two different 1D arrays. Like you have an X array, you have an array for X-axis values, you have an array for the Y-axis values, and then you just write a plt.plot X, Y. But here, since it's a two-dimensional array, I use the function called imshow. plt.imshow. It's basically shows each and every part of the array, like in the 2D array. So you can give it a color map. So color map is basically like whenever you visualize a two-dimension array, it's actually a three-dimensional function because at each pixel you have a third value of the brightness of that particular pixel. So to indicate the brightness, like how bright the source is, I want a color map. So if you just run it initially, you can see that my image looks something like this, where I'll just zoom it, or I'll just zoom it in. Yeah, so the image shows that the let's focus here. So this is somewhat lighter compared to these dark spots. The dark spots indicate the brightness of those spots is essentially zero, whereas the brightness here is crossing 500, which hits the maximum value, which is 552. So you can understand the the way we use a color map. So there are various ways of color map, like the basic one is gray, either black, gray, white, and so on. You can use various colors, like there are so you can just go to Matplotlib's website. You can see the various color maps available to use. Okay. Once we plot the image, I don't know, it looks somewhat messy. I mean, I can't see the nebula. Sorry, I'm not seeing a nebula. I can see whatever I'm looking at. Let's say I don't know the image I'm looking at. Let's say I don't know whether this is a nebula or a star cluster or whatever. So I don't exactly see my M42 here. So to understand why this happens, let's actually plot the histogram of this. So the histogram will help me identify the number of the brightness values for each and every pixels. First of all, I need to flatten this array, which I can just use data.flat, and then I just plot the histogram, and I see that most of the counts, like there are over 16 there are millions of pixels near zero, right? And it decreases considerably near, let's say around somewhere around 50 or so. There are very few pixels, and near the maximum value, which is around 552, there are hardly 1 or 2 pixels, that's all. So it's highly populated around around zero. So I want to change the scale. The scale here is just a linear scale. I'll just try to scale it to logarithm and see how the image looks like. So you can change easily to log using from Matplotlib colors. You can import log dom, which is the way to scale it to log, and then change the color bar a bit, like with some numbers which I put, which looks good. You can change it to see whichever suits you. You can use it, like you can vary this, but still the image doesn't look that great. But yeah, I can see the characteristic features a bit. So yeah, this is how you open a face file and see what exactly it contains and change the scale and so on. But my goal was to produce a RGB image. I want to make an RGB image because RGB image will look good, and we might be able to see a better image using an RGB image. To create an RGB image, we already have our data files, like we already downloaded the U band, the I band, and G band fits, which I already pasted in this particular folder which I'm using for my Jupyter notebook. Just open them. I'll just come to this later, like I'll just push it. So I just opened them. I opened it as like M42U, M42I, M42G. Now I'll just go back to where I started, where I said why exactly we are using Astrofile. So Astrofile contains a lot of lot of functions which will be useful to work, which will simplify our work in a better way. Like for example, if I want to make an RGB image without Astrofile, it might require lines and lines of code. But in Astrofile, you already have a function which makes RGB image for you. To get that, first of all, you need to go and import from the Astrofile.visualization module. Take the import make LUPTON RGB. So this is the function which we'll be using for getting the RGB image. So first of all, take the data and store it in different objects like G, I and U corresponding to them, G, I and U. And then it's just a matter of this function. I'll just explain what this means. So this corresponds to the R part of the image which I want to make. So I'll just send the particular wavelength which is the highest. In this case it is I, and then I'll send the particular image which has the lower wavelength. I mean, you can change and see how the image looks, but this is the best way to do it because you get a good RGB, proper RGB image out of it. So send them in the order RGB, and then you can use these functions stretch and Q. So it basically it plays around with the pixels and the sizes, the distance between them, and so on, and it makes the image better. I'll just run this first of all. You get something like this. Let's first of all change the stretch values and see what you get. Like I go back to 0.5, so you can see how it looks like. You can change and see whether it becomes better or worse. I think it's better. I mean, you are getting more features here and there, and then so if you then once you do this, you can just plot it using IMShow, and I have saved it here. Also note this, what will happen if I change, let's say, G and I? How does the image look like? I'll just open the image in another window so that you can compare them. This is the image. I'll just keep it here, right? Just zoom in. Oh, zoom in both windows. Okay, I'll just keep it here. Right, so this is my image when I used I, G, U in that order. Let's see what happens if I change it. Yeah, so you can see, but this doesn't look natural to me, but you can see the variation. Like here, so like these particular points are more reddish in color because they correspond to the I band image, and whereas these image here I'm putting I in the G portion, RGB, right? That's why I'm able to see the same feature in the green color. Okay, and similarly U. So I can change maybe I and U and see what happens. So you get a better understanding. Yeah, see. Again, this portion is bluish because that's the I part. Oh, I'm sorry. So I, G, U. Yeah, that's the image. Okay. Now you can work with any particular thing, any object you like, any object of your interest. It's really good to work with measure objects because they're really good to see through it from a telescope. So you can try to work out an RGB image of an arbitrary object and see how does it look like, and then compare it later. So I'm kind of happy with the image, how it turned out. It looks really good. Now this is the basic of handling fetch file in Astropile. Astropile has a lot of advanced features which I won't be going into. Maybe I can make a video in the future about that, but for now let's see another important feature which will be useful mainly in solving some kind of problems where you want to convert your coordinate system. So I'll just explain the basic coordinate system which we use in astronomy, which is the celestial coordinate system. So the celestial coordinate system has two two coordinates, the right ascension of the RA and the declination deck. If you remember, here I was talking about RA and declination, this search by object coordinates. The RA and declination for a given star is a unique classifier of that particular star. So I can use RN declination confidently whenever I want to search a particular star or something. They are defined in such a way that, suppose this is called the celestial equator, which is like basically you have the Earth's equator just projected to a bigger sphere. This sphere is called the celestial sphere. It's just the projection of the whole night sky around the globe into a bigger sphere. So that's a celestial sphere. So you have the celestial equator, you have the celestial north pole, which is over here. You have the celestial south pole, which is over here. Then you have a line called vernal equinox, and the vernal equinox is where you start your 0, 0. It's basically the origin of this particular coordinate system. So it's right ascension is 0, declination is 0. If you go to the right along the celestial equator, along lines parallel to the celestial equator around them, then it's called right ascension, which is here. This is the right ascension. Whereas if you go along a particular right ascension, then it's a declination. Basically, these lines are just the projections of your latitudes and longitudes on the globe to the celestial pole, and then you can see how you can measure the RA and the declination of a particular object. Okay. So to work with them, you can import the units. Astrofile has a module called units, which will help you work with units easily. Like you can work with units of like meters. I mean, you can work with constants. Sorry, not constant. I mean units. Like whenever you want to convert units from let's say CGS to SI, it's already inbuilt in Astrofile, so you don't need to work out the conversion by yourself. Okay, that's why I'm importing units, and then I'm importing coordinates, because from Astrofile coordinates I'll import the sky codes, which will help you give the coordinates of a particular object. So here I'm giving coordinates in various ways, various fashion. Like the first one is the basic way, like you can just give it the RA and the declination. Again, coming to the U, which is the units, I have to specify the units always in Astrofile. So here I'm using degrees, that's why I'm using U dot degree. You can also give it in this fashion. This is what I prefer. Just give RA declination comma, then put unit equals degrees. You can also give it in this fashion. This is the hour, minute, seconds. You can convert a degree into that. Yeah, so that's how you give the thing. So once you run C, you can see it's RA declination in degrees. If you want a RA value, you can just type C dot RA. C dot RA, if I want to convert into hour format, you can get the hour. You can also find the declination. Declination again, it's in degrees, minutes, seconds. You can convert into radians. Yeah, so it's all easy. You can also finally you can transform it. You can transform it into various other coordinates. So this is a particular coordinate system called the galactic coordinate system. When you want to measure extragalactic distances, you use the galactic coordinate system. You can just put C dot galactic, which will give you L comma B as this. L and B are like two angles, which will help you specify an extragalactic object. Just keep it like that. Okay. Then you can also transform into any catalog like FK5. So yeah, so this is the basics of Astrofile. So handling fits file is kind of difficult in Python, but it's effective in doing a lot of fun activities with it. Like you can stack images using Python and so on, which we might be covering those in a further video. But I just want to stop this discussion with mentioning there a software called DS9. Okay. So DS9 is a software. It's a popular software for visualization of astronomical data. You can actually open a fetch file in DS9 and work with it easily. Like, um, I I can open one and show you maybe. 1 second. DS9. So if you use DS9, which looks something like this, you can open the image. Yeah, over here. So I just opened the image which I have. I have to fish the image. Yeah, I found it. Okay, let's just open the G thing and see. Yeah, so this is what you see. I mean, you don't see much stuff, but you can do a lot of changes with it. Like, as we know, we can change the scale to log. It's zoomed out, so I'll just zoom. See, it's already way better than what we did in Python. You can change the scale from linear, log, power, square root, whatever. Log is good. You can then use this. You can change the color, and you can actually make an RGB image using DS9. Let us know if you want a tutorial on DS9. You will learn a lot from DS9 alone. You don't need a bunch of Python to understand this, and it's easy to work with. So yeah, if you want the tutorial on DS9, you can write it to us. You can write on the comment as well. Yeah, that's it for this session. I'll meet you in another session on Python for astronomy. Thank you.